Good evening, all of you. Is the AV clear to all? Thank you. So let us begin our today's session. So do you have any other queries with regard to the previous session on differentiability? What we have started earlier? Any queries from anyone? Say. Right. Then let us begin our today's session. So in our today's session, I want to take some problems on differentiability. Then we discuss about the mean value theorems, particularly the Rolle's mean value theorem. And then we do some problems based on Rolle's mean value theorem. So that was the tentative plan with regard to today's session. Fine. Is it clear? So please take a note of it. After noting, you please tell. Fine. Then let us begin with the problem that the function defined as f of x equal to mod x minus 1 plus mod x minus 2. You take this function. So for this problem, we are going to discuss about the continuity as well as derivability. So here, the interval which we consider is closed interval 0, 3. So on this interval, the function is defined as modulus of x minus 1 plus modulus of x minus 2, and we are going to check for the continuity as well as derivability for the interval. Okay? Is it clear? Now let us bifurcate the function values here. So let us substitute the values x equal to 0, x equal to 1, and x equal to 2. What will be the corresponding function values here? So if you take x is equal to 1, f of x will be 1. If you take x equal to 2, f of x will be 1, right? Now if you take x equal to 0, f of x will be 3, right? Now if you take the value of x which is lying between 0 and 1, what could be the function value? So whenever x lies between these two values, mod x minus 1 is nothing but 1 minus x, and mod x minus 2 is nothing but 2 minus x, as mod x is defined as if x is less than 0 and x if x is greater than or equal to 0. So since this part is negative, you take 1 minus x, this part is negative, we take 2 minus x. So f of x will be, if you calculate, accepted all, the value of f of x, tell. Do we agree for this? Now if 1 is less than x is less than 2, x is a number which is bigger than 1 and less than 2, then mod x minus 1 is nothing but x minus 1, and mod x minus 2 is nothing but 2 minus x. So if you consider the value f of x is nothing but accepted the value, right? Now if x is greater than 3, then the same values will be taken, x minus 1 plus x minus 2, it will be 2x minus 3. So this is about the bifurcation of the function. Any questions over this to anyone? Because since we are calculating limits and differentiabilities over the interval, yes, we take 2 to 3 also. Okay. Apart from this, we can simply take then it will be taken like this. Since we are not going beyond the interval. Okay? Right. Even though if you take greater than 3, the same values will come, right? Yes. So this will be the bifurcation of the function. So if you calculate for x is equal to 3, then f of x will be the value for x is equal to 3. 3, right? Now let us go with calculating the limits as well as the derivatives. So if we consolidate the total f of x values, then so 1 less than x less than 2, value is 1, x is equal to 2, value is 1, x is equal to 1, value is 1. So its value is 1 when 1 less than or equal to x less than or equal to 2. So when 2 less than x less than 3, its value will be 2x minus 3. And its value will be 3 when x is equal to 3. And for the value, if you consider you can take straight away. This will be the bifurcation of the function in a simple manner. Agreed? Right? Since you are calculating the continuity and differentiability for the function over the interval, since the bifurcation is done, that is also correct. Since if you put 0 straight away, we will get 3, right? That's why if you want to do a little modification, you can do the modification like this. Then we will write like this, so that we have a clear clarity over the entire thing. Fine. Since the bifurcation is done at the points 1 and 2, you are going to verify the continuity at the points 1 and 2, because before 1 and after 1 the function value is changing, before 2 and after 2 the function value is changing. Agreed? That's why we calculate the respective continuity and differentiability conditions at the points 1 and 2. So if you go for continuity, so limit x tends to 1 minus f of x, this will be limit x tends to 1 minus f of x will be 3 minus 2x. So the value will be 1. Accepted? Right. So let us calculate the right limit. Since left limit and right limit also function values are equal, it is continuous at the point 1. Agreed? In the same manner, you can verify that if you calculate the left limit and right limit at the point 2, the values are equal. Can you check on that? Left limit, right limit and function value at 2, the values are equal. Is it correct or wrong? Right. So if you calculate the left limit and right limit at the point 2, you are going to get the values are equal. So the function is continuous at the point 2 also. Now we are going to check the differentiability at these points 1 and 2. So if you calculate the left derivative, limit x tends to 1 minus f of x minus f of 1 by x minus 1, it will be equivalent to limit x tends to 1 minus f of x will be 3 minus 2x minus 1, f of 1 value is 1 divided by x minus 1. The value will be minus 1. So what is the function value here? You are taking the values from this part, right? Minus 2. Where it is minus 2, please tell. So do you have the question about the continuity at the point 2? Right. So if let us calculate the continuity at the point 2. Derivative value is minus 2. Right. I am going to write it as. I'm just writing. I'm checking for the short part. What you are going to mention, right? Just 2 common. So you don't have any questions with regard to continuity, right? The function is continuous at 1 and 2. Agreed? Right. Now we are calculating the derivative part. So if we calculate the right derivative at 1, since you are taking 1 plus, its value will be 1 minus 1 by x minus 1, the value could be 0. Right. Since left and right derivative values are existed and unequal, the function is not differentiable at the point 1. So in the same manner, if we calculate the derivatives at the point 2, left and right derivatives, we are going to get it as for 2 minus the value is 1, f of 2 is 1 by x minus 2, 0. For 2 plus, its value will be 2x minus 3, value 1 by x minus 2. So this will be 2. Agreed? All of you? So why I have taken this example? Because as we have studied earlier in the previous class that even though the function is continuous at the points, there is no necessity that the function would be differentiable at those points. So whenever you want an example that, give an example that the function is continuous at the points and not differentiable at the points, you can take this kind of example. Okay, because you know how to calculate the limits and how to calculate the derivatives. This example gives the other idea. So continuity is just a necessary condition but not sufficient condition so that the function will be differentiable at the point. Fine. Is it clear? Right. Then let us go with the other problem. Can I erase this? Okay. The other problem I am going to pick up is to take the function f of x is equal to x into sine 1 by x for x not equal to 0 and 0 for x equal to 0. Let us consider this example. Since the bifurcation is done at the point 0, so if you are going to calculate the continuity as well as differentiability at 0, then what happens? So can we say that the function is continuous at the point 0? Do we accept? If so, let us calculate the limit part that limit x tends to 0 minus f of x. It will be equivalent to, if you go with the style that limit h tends to 0, 0 minus h into sine of 1 by 0 minus h. Accepted all the value for calculating the limit part. I think you have the idea for calculating the limit like this. Agreed? Similarly, if you calculate the right limit also, the same answer will come. So the result is 0 here, because 0 into some constant will give the 0 value. Similarly, if you calculate the right limit is also 0. So you have the left limit, right limit and function value, all the three values are equivalent to 0. Hence, it is continuous at the point 0. Accepted? Any questions with regard to continuity to anyone? Please tell. Right. So if you calculate or if you check for the differentiability at the point 0, then So if you calculate the left derivative, limit extends to 0 minus f of x minus f of 0 by x minus 0, you are going to write it as limit h tends to 0. So 0 minus h into sine of 1 by 0 minus h minus 0 whole divided by 0 minus h. This will be equivalent to limit h tends to 0. Accepted? All? So, since the value is oscillating between minus 1 and 1, the derivative value will not tend to a unique number. Agreed? Yes or no? Similarly, if you calculate the right hand side derivative, the same value you are going to get, limit h tends to 0 sine 1 by h you will get. So plus h gets cancelled. Hence, in that case also, it is not going to give a unique number to us. It is oscillating between minus 1 and 1. Therefore, left hand derivative and right hand derivative values are not giving a unique number. Hence, we can say that the function is not differentiable at 0, but it is continuous at 0. Agreed? Any questions for this problem? Are you clear with this? So, do you need to calculate the right hand derivative too, or not necessary? Fine. Then one interesting thing you can consider with regard to this kind of question was asked earlier in UPSC. So you define the function that so you take f of x is equal to x power p into sine 1 by x for x not equal to 0 and 0 for x equal to 0. Now the question part is, if you want to say that the function is continuous and also derivable at the point 0, what could be the value of p? That was the question. If the function is defined in such a manner and it is given that the function is continuous at 0 and derivable at 0, it should be, then what could be the value of p? That was the question. Clear? How to choose p to say that the function is continuous at 0, and how to choose p the function is differentiable at 0. Okay, is it clear to all? Yes or no? So apart from sine 1 by x, you can take cos 1 by x also. Similar kind of question. So let us go with the solution part. Can I continue? Right. So if for going for continuity, so if you calculate the right derivative, right continuity, let me say, agreed for the right side limit value. Here the question is, For continuity, what is the value of p? For differentiability, what is the value of p? That was the thing. You treat it as two different parts. By combining the two things, we can at a time say that for continuity and to be differentiability, what is the common value for p? Okay, right. So do you agree for this right hand side limit? So if we calculate the left hand side limit, agreed all? Minus 1 whole power p plus 1, I can say h power p I will take. So do you agree for this limit evaluation? Any questions? Fine. Now, since the function is to be continuous, the two limit parts must be equal, right? And the values must be equal to 0. Because if I say that the function is continuous at the point 0, it means that left hand limit, right hand limit, and function value, all the three must be equal to 0. Sorry, all the three must be equal to 0, right? Yes. So the right hand limit as well as left hand limit must be equal and equivalent to 0. In such cases, what could be the value of p? Right. So except p is equal to 0, if you take any positive number, all the values will be equivalent to 0. Agreed? Because earlier you have calculated the limit part in the previous problem. So for continuity, for all p greater than 0, the function is continuous. That was the conclusion. Clear? Yes or no? Right. Since we are done with the continuity part, let us go with the derivability. So I am going to calculate the left hand derivative as well as the right hand derivative. Right. So if you have taken this, I will erase. Please inform if you have noted this. So can I erase? Right. So let us calculate the right derivative as well as left derivative. If you calculate the right derivative, it will be equivalent to limit h tends to 0, 0 plus h whole power p accepted this. the right derivative part. If you calculate the left derivative, agreed? I think 1 minus gets cancelled in the denominator. So you can write it as minus 1 whole power p into h power p minus 1. Because in the numerator you have minus 1 whole power p plus 1. In denominator you have 1 minus and h is there. So it will be h power p minus 1 and 1 minus gets cancelled. So minus 1 whole power p into h power p minus 1 into sine 1 by h. Agreed? Right. So to be derivable at the point 0, these two values must be equal. The right hand derivative as well as left hand derivative. So if you observe that the two derivative values, so what is the possibility that these two values are equal for what value of p? Any guesses? So randomly take that p is equal to 0, p is equal to 1 and p is equal to 2 and check whether they are equal or not. So are they equal when p is equal to 1? Are they equal when p is equal to 0? Are they equal when p is equal to 2? By substituting the p value here. Is the ideology clear for you? The derivative values must be equal. So if you take p is equal to 1, then are they becoming equal? Because if you take p is equal to 1, this will become 1 and this will become 1. This part is nothing but limit h tends to 0 sine 1 by h, and this is also similar, which is not giving a unique value. Say, isn't it? Yes or no? Right. So you cannot take p is equal to 1. So you can take the case for p is equal to 0 also. But if you take p is equal to 2, then since h power something is positive, so while calculating the limit, you always get that 0 into some constant. Whether you calculate the left derivative as right derivative. Since the value is becoming equal to 0, then we say that left derivative, right derivative both are equal. Because if you substitute p is equal to 2, then it is nothing but limit h tends to 0, h into sine 1 by h. This is equal to 0 into some constant. Accepted? Yes or no? Similarly, the same case is applicable for the left derivative also. Hence, the two derivatives are equal. Therefore, the function is differentiable when p is greater than 1. Any questions? So if you take p is equal to 0, then what will be h power p minus 1? It will be 1 by h, right? Right? It will be h power minus 1 sin 1 by h by 1 by h. So for the left derivative value, if you take that, if this will be p is equal to 0, is that acceptable? So what could be its value? Are they equal? Are they giving any unique value to us? So for p is equal to 0 and for p is equal to 1, you cannot have a unique value to get. Hence from p greater than 1 onwards, you are going to get that the derivative values are equal. Hence it is differentiable for all p greater than 1. So at the end, the conclusion will be taken as for all p greater than 1, it is continuous as well as differentiable at x equal to 0. For all p greater than 0, it is continuous at x equal to 0. That was the conclusion. Okay. Any other questions from anybody? Then let us do something different. Can I continue further? I am going to erase this. So let us take the problem that f of x is equal to sine log of x square or sine of log x square. Please take a note of it. So here also we go for the same discussion. We are going to discuss about the continuity and differentiability at the point 0 for this problem. Okay. So did you come across similar kind of problem earlier? Any one of you? All right. So let us start with the continuity. So we are going to calculate the left limit as well as the right limit. So if we calculate the left limit, it will be taken as agreed the value. Fine. Now if you calculate the limit value, since 1h is presented here, this will be 0 into some constant, because while applying h tends to 0, this value is going to oscillate between -1 and 1 sin log h square value. Accepted? So here k is a constant which is going to be oscillated between -1 and 1. Agreed? Similarly, if you calculate the right hand side limit, here also the same thing comes, 0 into some constant, where k is a constant which is going to lie between -1 and 1 sin of log h square value. Therefore, the left limit value, right limit value and the function value, all the three values are equal to 0. Hence, the function is continuous at 0. Clear? Any questions? So please take a note of it. Then we go for the differentiability at 0. So is the limit part clear, or you have a question with regard to limit part? All of you? Right. So let us go with the differentiability. Can I? So we are going to calculate the right derivative as well as left derivative. So if you calculate the right derivative, so which is not going to give a unique value, or which does not exist, you can take. Similarly, with the case, if we calculate the left hand side derivative, because h gets cancelled while applying the limit, which is not going to give a unique value. Therefore, the function is continuous at the point 0, but it is not differentiable at the point 0. That was the conclusion for this problem. Is the part clear? I think many of you have come across for similar kind of questions earlier while doing calculus problems. I hope so. Have you? That's why I'm not going to take much discussion on these problems. So, apart from calculating this derivative portion, let us do something different. That now the question arises that since we know whether a function is continuous and differentiable at a particular point, now what happens if you consider the algebraic properties? Since we have done similar discussion with regard to the continuity and differentiability of the problems, such that if f is continuous and g is continuous, if you add them, the result is continuous function. Agreed? Similarly, if you talk of the differentiability with regard to the algebraic properties like addition, subtraction, multiplication, division, etc., what can we say about that? If the functions are derivable, is the product derivable? Or if not, is it necessary that whenever the functions are derivable, then only the respective algebraic functions are derivable? Is the ideology clear to all? Yes or no? What I am going to say. Are you clear for it? Right. Now, let us take one simple example that you simply take the function as mod x. Now, is mod x a differentiable function at the point 0? No, because we have done it already. Mod x is not differentiable at 0. Right. You take the other function also same. You take f and g are same functions, mod x and mod x. Now, if you take the algebraic property like multiplication of these two, what will be f star g? The product, nothing but mod x whole square is equal to x square. Agreed? So, is the function x square differentiable at 0? Is the function x square differentiable at 0? Yes. Now, what was the one conclusion here? This is differentiable at 0, but these are not differentiable at 0. It means that for continuity, if the functions are continuous at the points, then the resultant algebraic functions like f plus g, f minus g, etc. are continuous at the points. But whereas for differentiability, the product will be differentiable or the algebraic function will be differentiable, but the individual functions need not be differentiable at the respective point. Okay? Is the logic good enough? Let us take one more similar example. Just now we have done it that f of x is equal to x into sine 1 by x for x not equal to 0 and 0 for x equal to 0. We have defined like this. So, is the function differentiable at 0? We have done right now. Is it differentiable? No, because you can take the conclusion that whenever you have a function of the form x power p, when p is greater than 1, then only it is differentiable. So if you take p is equal to 1, it will be just continuous but not differentiable. Agreed? We have made a discussion earlier. Right. Now, for the other function g, you take it as minus f of x. Since f is not differentiable, g is also not differentiable. Now, what happens if you consider the sum f plus g, it is nothing but the zero function, which is nothing but a constant function. Since a constant function is always continuous and differentiable, so if you conclude that the sum of the functions is differentiable at the point 0, but the functions are not differentiable individually at the point 0. Okay? So this is one good point we need to understand with regard to differentiability concept. You can find similar kind of examples with the problems we have done in exercises. So the main concern is, as and when you consider with the algebraic properties, the resultant functions may be differentiable even though individual functions are not differentiable. That was the whole idea. Fine. So do you have any other questions with regard to this property? Yes or no? then I want to go with the mean value theorems now. That will be interesting to all of you. Let us go with it. The concept of mean value theorems. Because we have done some of the problems with regard to the continuity as well as differentiability. Shall I? Fine. Because if you take the part, the focus is less given with regard to finding the limits and derivatives. The focus will be given on mean value theorems and problems based on its applicability of mean value theorems. Now let us begin with the Rolle's mean value theorem. I think you have come across with these problems earlier while studying in calculus, Rolle's mean value theorem, Lagrange's mean value theorem, and Cauchy's mean value theorem. How many of you are learning for the first time? Right. Then straight away I go with the point that if you take the statement of Rolle's mean value theorem, you are going to take a function on closed interval AB to R, because closed interval is sufficiently very large. So the property is it must be continuous on the closed interval and derivable on open interval, and f of A and f of B must be equal. Some others have defined that they are equal to 0, but usually it is taken that f of A is equal to f of B. Then on the interval what you have considered, between A and B, you are going to find at least one point C such that f dash of C is equal to 0. This was the statement of Rolle's mean value theorem. So if you have known that, it is okay. Otherwise, please take a note of it. If f is a function defined from closed interval AB to R, having satisfied with the three properties, then you are going to find at least one point C which is bigger than A and smaller than B, such that f dash of C is equal to 0. Fine. Is the statement clear? Now, one interesting thing is, what is the geometrical perspective of this Rolle's mean value theorem? For a graph, if you have considered, if you have taken a continuous graph, what is the geometrical significance of this Rolle's theorem? Anyone has any idea? Please tell. Is anyone has any idea with regard to the geometrical perspective of the Rolle's mean value theorem? How it looks like geometrically, and what is the significance of this? Not cutting x-axis. Here you are not saying that f of C is equal to 0, you are saying that f dash of C is equal to 0. So what is the importance of derivative with respect to a graph? Nothing but a tangent, right? Yes. So it is nothing but whenever you draw a graph and you say that this is the interval AB, I have taken it in the first quadrant. So if this is the graph, then you can say that in this at least you can find one point C such that if you draw a graph, if you draw a tangent at this position, the tangent is parallel to x-axis. At the point C, it means that there you have possibility of at least one. then you will have different possibilities that, suppose if you have taken the graph like this in a manner, this is my graph, then you have 3 different points within the interval, that if you consider the tangents at these points, the tangents are parallel to the x-axis. Okay. So the importance is, in the interval at least you can find one point which is parallel to x-axis if you have drawn a tangent with regard to that point. Clear? The geometrical perspective. And we have some violations with regard to the Rolle's mean value theorem, that even though a function is discontinuous and etc., in such cases also you can find a point within the interval such that f dash of c is equal to 0. Clear? Are you getting the idea or not? So have you noted this? Then I will go with the problems and giving one small example with regard to the violation of Rolle's mean value theorem. Right. Since the function is to be satisfied, continuous, differentiable, and f of a, f of is equal to f of b, even though these conditions are not satisfied, we can say that we can find a point within the interval such that f dash of c is equal to 0. It is simply taken, any kind of example you can take. One simple example you can consider as, so let us define, you take the closed interval 0, 2, f of x you take it as 1 and x plus 2. Let us define the function like this. Now, is the function continuous within the interval? Because I am asking about that limit extends to 1 minus and limit extends to 1 plus, are they equal? So it is not continuous. Obviously, if you take that the points f of 0 and f of 2, are they equal? No. So obviously the conditions of Rolle's theorem are not at all satisfied. But if you calculate for f dash of x, since differentiation of the constant is 0, so from 0 to 1 you have so many points in the interval such that the chords are parallel to x-axis. Agreed? Yes or no? So this is one kind of example that you can take with regard to the failure of Rolle's mean value theorem. Not only this, you can take any kind of function where a bifurcation is required. Suppose if you have taken that this is 0 and this is x plus 3. In such case also, Rolle's mean value theorem will not be satisfied, and you can say that you can have so many points such that chords are parallel to x-axis. Accepted? Right. Then let us take one interesting problem, the applicability of Rolle's mean value theorem in deciding the nature of roots. So can I take the problem? So here is the question. I think you have already done it with regard to the calculus problem. For the function or for the equation, x cube minus 3x plus k equal to 0, please take a note of it, the problem. I think you have done similar kind of question earlier while doing calculus. If you have known this, let us omit this problem. Have you done it earlier with regard to Rolle's mean value theorem? Then let us have a discussion. So the problem says that if you observe the equation x cube minus 3x plus k equal to 0, you can take any real number in place of k. You take k is equal to 1, k is equal to 2, k is equal to 3, k is equal to 0.5, etc., etc., etc. You can substitute any real number in place of k. Since it is a third degree equation, how many roots you can find for it? 3 roots, isn't it? Because it is a cubic equation. So if you have calculated the roots, if you have counted all the 3 roots or calculated all the 3 roots, you cannot find 2 different roots which are lying in the interval 0, 1. It means that if you have said that A, B are 2 roots which are different and which are lying between 0 and 1, it is not possible practically. That was the statement resolution. Is that okay? The concept of the problem? You can substitute any number k. If you calculate all the roots, you cannot find 2 different roots which are coming in the interval 0 and 1. Clear? Right. Now, to prove this problem, let us assume it contrarily. So let us say that there existed some k such that in the interval 0 and 1, I got 2 roots for the equation x cube minus 3x plus k equal to 0. Let us assume that. So I have found a real number k such that if I have calculated the roots of the equation x cube minus 3x plus k equal to 0, I got 2 distinct roots, let us say alpha and beta, where alpha is smaller, beta is bigger, let us assume, and these 2 roots are lying between 0 and 1. Now let us apply Rolle's theorem for the given function. Since it is a polynomial function, it is continuous on the given interval 0 and 1. Since it is a part of it, it is continuous on closed interval alpha comma beta also. Since you can find the derivative, because its derivative is 3x square minus 3, so it is differentiable on the open interval 0, 1 and hence on the open interval alpha comma beta. As you have taken that alpha and beta are roots of the equation, so if you say that f of x is equal to x cube minus 3x plus k, you have f of alpha equal to 0 and f of beta equal to 0 because they are roots. So the given function is continuous, derivable and having endpoints as equal value on the small interval alpha beta. So f satisfies Rolle's mean value theorem on this small interval. Any questions so far? To anyone? say. Right. The question is, I am going to apply the Rolle's mean value theorem for the given equation. As per the mean value theorem concerned, the function must be continuous, differentiable, and having endpoints has equal value, isn't it? It is a polynomial function, x cubed minus 3x plus k, hence it is always continuous, because every polynomial is continuous always on the whole real number system, every polynomial. So it is continuous on the given interval, hence it is continuous on this small interval also. Agreed? And it is differentiable, because what is the derivative of f of x? 3x square minus 3. So it is differentiable on the interval alpha beta, the open interval alpha beta. Since alpha beta are roots, they satisfy the function f. So f of alpha is 0 and f of beta is 0. It means that for the interval, endpoints have same value. F of alpha is equal to f of beta. Okay? So in this way, the three conditions of Rolle's mean value theorem are satisfied by the function f in the small subinterval alpha beta. Agreed all? Any questions, please? So, did anyone has any questions? Please tell. Are you getting the idea? Right. Now, as per the Rolle's mean value theorem is concerned, you are going to find a point, at least one point, C, which is lying between alpha and beta, such that f dash of C is equal to 0. So if you calculate f dash of C, it will be 3c square minus 3 equal to 0, implies c square minus 1 equal to 0, implies C is equal to plus or minus 1. Accepted? Now what happens here? As per the variations are concerned, you have 0 is less than, alpha is less than, C is less than, beta is less than 1. So, as per the problem is concerned, C must be either plus 1 or minus 1, which does not belong to the interval which is specified here. So, since Rolle's theorem is always correct, so our so far assumption is wrong. You are getting a contradiction here. Because if C exists, C must be here, but it is not practically possible. So you are getting a contradiction. Why you got a contradiction? Because you have assumed that there existed a number k. At this point you got the contradiction. So there is no number k such that you can find two distinct roots within the interval 0 and 1 for the equation x cubed minus 3x plus k equal to 0. Okay? Is that clear? Any questions, please, to anyone? Did you get the logic? If anybody has any other questions, you please tell. Otherwise, I will take the next problem. Please take a note of it. Can I continue? So this is the problem. So please take a note of the function. F of x is defined by x minus a whole power m into x minus b whole power n, where x is a point taken in the interval ab and m comma n are positive integers. Now the question is, discuss the applicability of Rolle's mean value theorem. That was the question tag. So here, discuss the applicability means we need to check whether all the three conditions of Rolle's mean value theorem are satisfied by the function f of x in the given interval ab. If it gets satisfied, then you need to find what is the value of c in that interval. Okay? Is it clear to all the objective of the question? Are you getting or not? Right. Now let us begin with the checking conditions. We have x minus a whole power m is a polynomial if we expand it by means of the binomial theorem, and x minus b whole power n is also a polynomial. Every polynomial is continuous on the number line. So this is a continuous polynomial, this is a continuous polynomial. So if you consider the product, it is a polynomial of degree m plus n. So it is continuous, and in particular it is continuous on the given interval. Okay? Anybody has any issue with regard to the continuity? While writing exam also we do the same thing. We explain the thing in words, not by calculating the limits. Since it is a polynomial, the other one is a polynomial which are continuous. Hence the product is a polynomial of degree m plus n. So obviously it is continuous on the number line, and in particular the interval which you have taken. Okay? Agreed or not agreed? Now let us check for the third condition. For the interval AB, you calculate f of a and f of b. So if you substitute x is equal to a, its value will be 0. If you substitute x is equal to b, its value will be 0. So f of a and f of b are equal, because f of a is equal to 0 and f of b is equal to 0. Agreed? Now let us go with the derivative part. So if you calculate f dash of x, please understand there is no need to say it is derivable, because every polynomial is differentiable, isn't it? So automatically it is differentiable. As and when the polynomial is continuous, it is differentiable. Right. So let us calculate f dash of x. If you consider the value, it will be m into x minus a into m minus 1 into x minus b plus x minus a whole power m into n into x minus b whole power n minus 1. So if you take common the values, x minus a whole power m minus 1 into x minus b whole power n minus 1, it will be agreed the value. I have applied the product rule. So this will be equals to x minus a whole power m minus 1 into x minus b whole power n minus 1 into m plus n into x minus of mb plus na. Now this is the derivative value. Now what happens? F satisfied the three conditions. You have written it is continuous. You have written it is differentiable because it is a polynomial, and f of a, f of b have equal value. So it has satisfied the Rolle's mean value theorem. In other words, Rolle's mean value theorem is applicable on the given interval. So as per Rolle's mean value theorem, you can find a point C such that f dash of C is equal to 0. So if you make the derivative value as 0, that means this product equal to 0, and if you put x is equal to C there, then you have m plus n into C minus of mb plus na is equal to 0, implies C is equal to mb plus na by m plus n. This is the value of C. In other words, you can say that C is a point which divides the segment AB in the ratio m is to n internally, because we have taken this kind of relation earlier in coordinate geometry. Please check. And from the derivative value itself, since you are making derivative equal to 0, so this part will be equal to 0, this part will be equal to 0, this part will be equal to 0. So if you put x is equal to C here, you will get C is equal to A. If you put x is equal to C here, from this part, C is equal to B. Since as per Rolle's theorem, the point is lying in between A and B, so you are not considering these things as the result of C, and you are considering to find C. This is the only part under consideration. Okay. So as per Rolle's mean value theorem, the value of C is mb plus na by m plus n. In other words, C is the point which divides the interval AB in the ratio m is to n. That was the conclusion. Now let us take one small thing, that suppose I have given f of x is equal to mod x on the interval minus 1 comma 1. Is Rolle's theorem applicable here? No, because mod x is a continuous function, but at the point 0 it is not differentiable. Hence Rolle's theorem is not applicable for this problem. In a simple example, let us take one small problem. There is no need to give a brief discussion on it. From the very problem, on seeing it, you can say whether Rolle's theorem is applicable or not. The problem is, if you have taken the interval closed interval 0 2, and if you have taken f of x is equal to 2 plus x minus 1 whole power 2 by 3. That was the problem. So is the Rolle's theorem applicable for the function f of x on the interval 0 2? Then the question is no. Why? Because if you consider f dash of x, the derivative, so it will be 2 by 3 into x minus 1 whole power minus 1 by 3. Is that right? The value? If you calculate the derivative. Right. So if you observe the differentiability of the function in the interval 0 2, at 0 it is differentiable, at 2 it is differentiable, at 1 the derivative becomes undefined. So to get that Rolle's theorem is applicable, at each and every point within the interval it must be differentiable. In particular, excluding the endpoints, if you take any point in between 0 and 2, it must be differentiable. That is the condition of Rolle's theorem. So 1 is a point which is lying between 0 and 2. At 1, f dash becomes undefined. So Rolle's theorem is not applicable for this problem. But the function is continuous on the interval 0 2. Okay? Any other questions, please, to anyone? So let us take one or two interesting problems on Rolle's theorem in the next session. Now let us conclude our today's session here, and tomorrow we will take problems on Rolle's mean value theorem as well as Lagrange's mean value theorem. So if you have any other queries, you can come up now. Any queries to anyone? So is the discussion sufficient for you in getting the understanding over Rolle's mean value theorem? Because I feel that many of you have studied the Rolle's mean value theorem earlier in calculus part. That's why straight away I have taken the typical problem, apart from taking a polynomial in the first discussion. Fine. Is it okay to all? And I have given a posting with regard to the problem which is asked, limit x tends to infinity, root x is equal to infinity, using the technique of delta and epsilon, as one of our friends asked. So do you convince with that answer which is posted there? Right. This problem you are asking? Yeah. Here the function on the interval -1, 1 is continuous, because mod x is always continuous. But at the point 0, it is not differentiable. So left hand derivative, right hand derivative, both are existed and they are unequal. So the function is not differentiable at the point 0, but it is continuous at 0, hence Rolle's theorem is not applicable. Okay. So any other queries with regard to the posting which is given there? Prior I have given the definition there. How do we define limit at infinity with regard to the epsilon and delta technique? Have you read that? The definition. So let me give one simple point, that if you say that the limit is finite, the underlying idea is very simple. In one simple thing, if you are checking the limit part with regard to a finite value, you consider a neighborhood that the value is approaching here. As the value x approaches a, you are checking for f of x is approaching f of a or not, isn't it? Say, right. So if you write that limit x tends to infinity, it means that x is going bigger, not to a finite value, isn't it? X is goes on increasing. It means that apart from taking neighborhood, if you fix a number delta, as x is going greater than delta, is corresponding f of x is fixed or varying. If f of x is varying means it is tending to infinity. If f of x is fixed means this fixed value is nothing but limit. Accepted? Right. So it means that if you have taken that for x greater than or equal to delta, mod f of x minus L is less than epsilon means x is goes on increasing and f of x is tending to a finite value. So it means that as x tends to infinity, f of x is tending to a finite value. If we have taken it is greater than epsilon, so f of x is violating L, so it is tending to infinity. Okay? Clear? So in this way, since you cannot write mod f of x minus infinity is less than epsilon, to avoid that technique, it was given that as and when x is goes on increasing, you check for f of x. If you have proved that f of x is always greater than epsilon, then it means that mod f of x is always greater than epsilon. It means that the function is tending to infinity. In other words, you are drawing a relation between delta and epsilon. Since x is greater than delta, if you say delta is greater than epsilon, as x is tending to infinity, if you have proved that f of x is greater than epsilon means f of x is also tending to infinity, isn't it? Please check on the picture. If you have taken x is greater than delta and delta is greater than epsilon, as x is tending to infinity, f of x is tending to infinity because you have proved f of x is greater than epsilon. That was the whole idea in proving that. Okay? I think that will give you an idea. Fine. So I feel that the answer, I am going to find another method by putting L. Let us find that. Right. Thanks to all. So let us wind up our discussion here. Tomorrow we will meet with mean value theorems. I think those sessions will be very interesting with regard to mean value theorems.